let us discuss the effect of temperature and stress on creep. So, effect of stress on creep is similar to the effect of temperature. So, if this test is suppose done at a stress sigma 1, and if we now conduct a stress at another a test at another stress sigma 2 greater than sigma 1, then the initial strain will be more. At the same time, the steady state creep rate will be higher, and finally, the creep life will be shorter. So, if we have, let us say, a creep life of Tf1 at sigma 1, then the creep life Tf2 at sigma 2 is shorter. So, Tf2 is shorter than Tf1, but the steady state strain rate, which is the slope in the steady state regime, is epsilon steady state at sigma 1. This is less. With increased stress, the slope increases. This is a steady state strain rate at sigma 2. So, steady state strain rate at sigma 2 is greater than strain rate at sigma 1. This stress dependence and the temperature dependence can be given as an equation. So, here is the equation: steady state strain rate depends on the stress and temperature. The temperature dependence is the familiar exponential dependence. You can see here exponential minus q by RT, where T is the test temperature in Kelvin. Of course, in these equations it is always in the Kelvin. Q is the activation energy. So, this will be the activation energy for creep, and R is the gas constant. So, exponential dependence on temperature. The stress dependence is like a power law. So, it is stress to the power n, n is called the stress exponent. So, it is some power of stress, n generally varies from 1 to 8. So, I can write it here. N is 1 to 8 depending upon the different creep mechanisms which we are going to discuss. So, the creep rate, steady state creep rate, is a strong function both of stress and temperature. So, a slight increase in stress and a slight increase in temperature can significantly enhance the steady state creep rate, and thus dramatically can reduce the creep life. So, creep is a very stress and temperature sensitive process.